Okay, I hope you can see the screen.
Yes, we can see it. Now make it full screen, please.
Yeah. All right. So,
It's not visual now, the screen.
oh,
It got out.
thank-
Yes, full screen mode.
okay. Is it good now?
No, same as blank screen.
Just wait for a second, Rameshwar.
Okay.
Actually, when it is not full screen, we are all able to see it. But as soon as you click the full screen, it simply either disappears or it is now the blank black screen.
Okay, let me do that again.
Yes.
Yeah, this means again because it is still not
Oh,
in full screen mode. So try one more time, and if it is not going to work, then we can continue with this mode only. Mhm. Yeah, so the slides are visible. Now try one more time with a play.
do you see that? No.
No, the situation is again hanged.
Says your screen sharing is paused. Hmm.
Yeah, Rameshwar, I think the font sizes are good enough. If it is creating trouble, you can start with it only.
Okay, do you see the screen now or no?
Yeah, we do see the screen. Can you change the slide once? You have to click them.
Yeah. Is the screen changing?
No, 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 it is not changing because something got hanged. Just unshare and reshare it again, please.
Okay, so bear with me.
Yes, can you change the slide? Yeah, the slides are changing, Rameshwar. I think the font size is good enough, so you can continue something like this.
Okay.
You can play once.
Okay, let's try one last time. No, it's your screen sharing is paused. So you don't see the screen now?
No, it is again the same hang situation.
Ah, okay.
But it's good enough, Rameswar. You can start.
Yeah, but then this will not move. He has to unshare and reshare again.
Do you see slide changing?
No slide changing. Uh, it is like last time. You unshare, you share, and then slides will change. Continue then.
Okay. Ah. All right. Do you see the slide now? I think
Yes,
you can go ahead.
Rameshwar, it is moving as well in this situation. Please continue. Yeah.
Okay. Thank you very much. And sorry for this technology mess. Um, as said, Dr. Amelia, thank you very much for your kind word of introduction. And so today, again, thank you very much. Giving another opportunity to present my work on physics of improved confinement in negative triangularity tokamaks that I have gathered over past couple of years. So I to this audience, I don't need to say why fusion is important, and given the current scenario of almost we are heading towards World War III and energy crisis. So fusion is uh, more important than ever these days. So it's time to accelerate the fusion research and achieve the goal that we had been running behind since, I guess, more than 7 decades for now. Uh, anyway, so this talk is dedicated to physics of improved confinement in negative triangularity tokamak. Negative triangularity concept has recently been very popular and attractive. And even though I'm sure many people in the audience know about what negative triangularity is, but assuming a broad spectrum of the audience, I would like to start with defining what a negative triangularity is and to really fix the audience. So earliest tokamaks had been in circular cross sections, like beginning in 1950 and 60s. But now a wide variety of flux surface shapes are possible. And the master in this is the pioneer in flux surface shaping is the TCB tokamak. They can achieve almost any flux surface shape you propose. It's another point whether those shapes have required magnetohydrodynamic and microscopic stabilities for useful fusion. In any case, the flux surface shapes can be easily parameterized by so-called Miller's parameterization. In this equation, you see the delta, which is a local function of the radius, is called the triangularity. And positive triangularity refers to positive D-like shape, which is the structure at the bottom. And the negative triangularity flux surface shape tokamak is as shown on the top plot. So here we are interested. The conventional tokamaks had been run in positive triangularity shape so far and at high elongation. But recently, and not so recently, in fact, it has been at least 2 decades now, the benefits of negative triangularity over positive triangularity has been uh, realized. And so everyone is now moving towards negative triangularity fusion concept. A bit in more detail, why negative triangularity? So high fusion gain relies on high pressure and high confinement time. And a reactor needs to achieve high normalized beta, at least greater than 3 to satisfy the Trion limit, and confinement factor greater than 1 simultaneously to qualify as a reactor. Positive triangularity H mode discharges have achieved this parameter, but at the cost of ELMs. And so for bigger devices like ITER, the size of ELMs are expected to be bigger. And so the plasma-facing components are expected to undergo strong degradation after each run. So alternatives are required. And negative triangularity turns out to be a natural um, a plasma shape which is devoid of large elms at a strong negative triangularity shaping. So recently, positive triangularity, H mode-like pressure and confinement has been achieved in L mode negative triangularity shape in D3D. So as I said, it's a natural scenario without elms. The power degradation is very weak. Fluctuations are reduced in negative triangularity. At the same time, the heat flux load width is wider, so amount of heat in each elm crust it receives is much less. So I mean the heat is spread on the plasma facing on the diverter plate, so diverter plates are relatively safer. And it has also been found that the NT supports reduced plasma wall interaction. So impurity recycling into the plasma is reduced by negative triangularity. So these qualities are promising, and so NT is now seen as a promising candidate for negative for future reactors. First demonstration of improved confinement in NT is from TCV experiments back in 2007. And improved confinement in NT over PT experiments is now well established over a wide range of parameters. So the figure that you see here is the canonical picture showing improved conductivity. I mean, reduced electron heat, turbulent heat conductivity for negative triangularity compared to positive triangularity, especially in weaker collisionality limit. So, notice that the TCV machine is strongly electron cyclotron heated, and so the electron to ion temperature ratio is 2 or greater than 2, and in such case, the trapped electron mode turbulence is dominant. And so immediately a few years later, explanation was sought for why TCV NT is less conductive than positive triangularity shape. And because of strongly electrocyclotron heated, it is dominantly trapped electron mode turbulence driven. And so TEM stabilization becomes a natural candidate for explaining why confinement is better in TCV NT. And TM stabilization is very easy to understand. It's because of precession drift reduction by negative triangularity. A decade later, D3D experiments demonstrated improved confinement in NT. Here we see the fluctuation spectrum, frequency spectrum of density for positive and negative, the negative in blue, the positive in red, and the figure in the middle is for temperature fluctuation. You can also see that temperature fluctuations are lower in negative triangularity. And on the right, I'm not sure if you can see the plots clearly, but at least what you can gather is the normalized beta is approaching 3 with time as NBI heating goes up for fixed ECH power. Also, the confinement the H98 factor goes above 1. So it shows H mode like confinement in L mode negative triangularity at a strong NBI heated negative triangularity plasma in D3D. Now, Is the confinement physics same as for TCB here? No, because it's strongly NBI heated, and in such case, also density is higher compared to TCB. So in such case, um, the electron to ion temperature ratio is close to 1, so electron and ions are equilibrated. And this situation is most favorable for ITZ kind of turbulence. So we need to understand how shaping affects ITZ turbulence, what regulates the turbulence in transport caused by ion temperature gradient driven instabilities in a strongly heated NBI regime. So this is the main motivation here. The ITZ turbulence in transport for NT remains poorly understood in the sense that same code and similar parameters have produced conflicting results in the past. And I can go into details of that later if you have questions, but there is no point in wasting time in looking at those in detail. But we know that ITC turbulence is saturated by journal flow shear, and we know this very well since many, many decades. The question, however, remained kind of unresolved till date is what saturates the journal flow shear in the collisionless limit. And the collisionless limit is the limit of interest for future machines because they will be very strongly heated, will be extremely less collisional. The core would be completely collisionless in ITER. So collisionless saturation mechanism of journal flow shear is extremely important to understand. And so understanding how shaping affects ITG turbulence leads you to face the question of how journal flow shear saturates in collisionless regime. And often Kelvin-Helmholtz-like linear instability mechanism is invoked to explain the stability of the journal flow shear. However, it's not hard to understand or imagine at least that the KH, at least the linear KH-like picture is questionable in turbulent setting in which the journal shear layer is itself time dependent and fluctuating over time. So this work or presentation has kind of dual intent. The first is to shed light on the collisionless journal flow saturation and leverage on that to explain the improved confinement in negative triangularity. So we are aiming for a nonlinear, completely nonlinear explanation of improved confinement in negative triangularity rather than the usual story of going behind just looking at linear instabilities, which anyway doesn't matter at saturation. So here is so to tackle these questions and to answer to some extent, I used gyrokinetic flux tube simulations called GENE. The simulations were run in the collisionless limit, but you cannot get rid of numerical dissipation. So the choice of parameter is such that it is a standard GA, I mean, general atomic parameters plus shaping. And before I go ahead, I must remind this is a physics study and not an experimental validation exercise. So in this study, the triangularity and the temperature gradient is varied. The resolutions are given here. Since there is no collision, explicitly collision added, so there is no frictional damping of the journal flow. And also there is no neoclassical physics included. So before I go into the details of the work for the restless, here is the key takeaway. So the finding is that the journal shear layers are highly dynamic. They form, evolve, merge, split, migrate, and decay. And the journal mode appears due to forward transfer of so-called free energy from turbulence to the journal mode due to negative turbulent viscosity. But at the same time, there are intermittent back transfer events, which transfers energy back from the journal mode to the turbulence. And that is an indicator of a nonlinear damping mechanism at play. So we'll realize that these back transfer events limit the stability and coherence of the journal flow shear in turbulent setting. So the real picture is more subtle than the usual tertiary linear KH instability picture. And especially when you are above marginality, the linear KH picture uh, uh, goes to the sink because of strong turbulence. We'll see that the reduced back transfer of free energy from journal mode to turbulence leads to more resilient and coherent shear pattern. And near marginality, the back transfer is suppressed. As a result, the journal shear coherence drastically increases. So the shear layers are more coherent near marginality. Now, this basic physics can be used to understand, to better understand what mitigates ITZ turbulence and transport by negative triangularity. So the reduced heat diffusivity for NT is because of increased effective shearing. And the increased effective shearing turns out to be due to enhanced coherence of the journal shear for negative triangularity, which is again due to reduced back transfer of free energy from the journal mode to turbulence. So the enhanced effective shearing for NT is because the shear layers are more resilient, and that's because of the enhanced coherence of the shear. At the same time, NT turns out to be a state with low journal kinetic energy but high journal shear, whereas PT turns out to be a state with high journal kinetic energy but low journal shear. So journal kinetic energy is not synonymous to journal shearing effect. Also, the stronger self-generated journal shear for NT is seen despite the low residual journal flow potential. Often residual potentials are used as proxy for the saturated state of shear, but it turns out residual potential is not a faithful proxy for saturated state shear. And so there is a whole industry calculating residuals for different situations and claiming prediction for nonlinear state, but those all turned out to be not faithful. So before we go into the nonlinear calculations, here is a quick look at, of how linear stability is affected by switch of triangularity from positive to negative. So the growth rates are reduced for negative triangularity, as well as the critical gradient is enhanced. And this is because the eigenmode structure and the magnetic drift frequency structure across the poloidal angle. So the eigenmodes are narrower for negative triangularity. As a result, the effective curvature drive is weakened due to less sampling of the bad curvature region. Alternatively, one can also understand the improved linear stability in negative triangularity by looking at the local magnetic shear structure in the pallidal direction. So the figure at the bottom shows that the depth and width of the negative local magnetic shear well in the bad curvature region increases for stronger anti-shapes. And that enables easier twist of edges towards the good curvature side as you move along the fill line, and that means a better stability for anti. So now we move to nonlinear and turbulent heat flux calculations. So figure on the left shows the heat flux and the heat flux diffusivity across triangularity. As you can see, for extreme triangularity, like plus minus 0.6, the heat flux is almost half of the heat flux for negative triangularity. On the right plot, you see the KY spectrum of the heat flux, and it shows that high KY contribution, that is the right-hand side of the spectral peak, they deplete more for negative triangularity. But wait, the heat flux is decided by amplitude and the cross phase. Okay, so the question is, which is the dominant mechanism in reducing the heat flux? Is it the amplitude reduction or the cross phase effect? So that we see here, the pictures on the top, so the KY spectrum of the PDF of the cross phase, that is phase difference between temperature and potential at a steady state. On the left is that for negative triangularity, the middle picture is for delta zero for the circular case, and on the right side is for positive triangularity. Now, the immediate impression that comes from these pictures is that, oh, they look almost similar, right? So there is no great effect of triangularity on the cross phase. The picture on the bottom shows the fluctuation kinetic energy versus triangularity, and you can clearly see the fluctuations are stronger for positive triangularity than for negative triangularity. So the conclusion here is that transport reduction for negative triangularity is predominantly due to reduction of fluctuation amplitudes. Next, we characterize further the fluctuations, calculated the autocorrelation, length and time. The picture on the left is the autocorrelation for the fluctuation. So that's the autocorrelation time, figure A. Figure B is for the autocorrelation length. And the third picture on the right gives the random walk diffusivity. So what you see is that the autocorrelation time is higher for negative triangularity than for positive triangularity. At the same time, the radial autocorrelation length is lower for anti. As a consequence, the random walk diffusivity is lower for anti. And this has previously been reported in TCB experiment and more recently last year in D3D measurements. So at this stage, one wonders why the radial autocorrelation length is reduced by negative triangularity, and the smoking gun is the shearing effect. So next, we look in detail the spatiotemporal pattern of the John Lee Crosby shearing rates. Again, on the left, you see the shearing pattern for negative triangularity, in the middle for circular case, and on the right for positive triangularity. So as you can see, the spatiotemporal pattern is highly sensitive to delta, and the pattern is more coherent for negative triangularity than for positive triangularity. Compare the cases on the left and on the right. Also for circular case, you see propagating shearing fronts. These are dispersive feature for delta zero, and the front speeds scale with the diamagnetic velocity. So at this stage, you already get the impression that more coherent spatiotemporal shearing pattern for NT would lead to stronger mean shearing effects. And so we quantify the zonal shearing rates at the saturated state. And the figure on the left shows the radial wave number spectrum of the zonal shearing rate, time average zonal shearing rate. So it is zero frequency zonal shearing rate. And the blue one is for NT, the red is for PT, the black in between is for zero triangularity. You can see the peak shearing for NT is stronger than for PT. However, if you look at the zonal potential, you see the opposite trend. So the potential doesn't matter, but how potential is distributed across the scales that leads to the shearing effect. That's the important quantity. So picture on the right top shows the RMS shearing rate versus triangularity, which shows that RMS shearing rate is higher for NT than for PT. So all this analysis leads to conclusion that ITG transport reduction is due to enhanced zonal shearing rate in NT. And the figure here on the right shows the black curve is for heat flux diffusivity, and the blue and red curves are effective zonal shearing rates. So red one is shearing rate times the autocorrelation time of turbulence, and the blue one is shearing rate divided by the maximum linear growth rate. So both gives a similar trend of effective shearing versus triangularity. So the key to improved confinement in negative triangularity is the enhanced shearing effects, and that is because of the enhanced spatiotemporal coherence of the zonal shear. All right, so before I go on, I would like to pause here for a minute and see if there is any question so far. Because now will be a slightly change in gear. So Ganesh has... Okay, Ganesh wants to talk, yeah. Hi. Ganesh, go ahead.
Yeah. Your model electrons are adiabatic, right?
Yeah.
Okay. So in when you think of so far I understand is that your main projection for betterment is that the zonal once the zonal flows are formed and they have certain structure, it doesn't further destabilize and go back to a regular finite MN mode, go back to the turbulence in the NT case. Whereas in the PT, there is also a back reaction between the zonal turbulence, the zonal flows and the regular turbulence. Is that correct?
That's partially correct, yes. But we are going to that point in more detail. in subsequent
Right.
slides.
All right. And how do you, in your previous, if you go to slide number 16,
Yeah, we are on 16.
uh, okay, I think I'm seeing a little later. Oh, maybe slide 14, two slides before.
Okay. Yeah, this one.
Yeah. So I really don't see a big difference between the PT and NT unless I'm missing out some aspects here. I see fronts uh, propagating fronts in both cases. And should I look at the uh, number of such fronts increasing? How do I see the difference between the NT and the PT case?
Yeah, good question. So in anti case, you see the fronts are more, more straight. Okay, they are less radially propagating. Plus, the front, as you can see from the structures, already the coherence time seems to be bigger, right? If you look at uh, the the size of these say positive shear, the red structures, the length in time is much bigger than those for PT, right? So
Okay,
the
I
shearing
think
pattern,
I'm used to seeing probably X or the length on Y-axis and time on X-axis. So,
oh
so that the slope is automatically the shear front speed.
yeah.
Okay,
So
okay, okay, okay,
the
fine.
x-axis is really the x coordinate here, the radial coordinate, and
So
y
the
is the time.
slope is not the velocity; it's inverse of velocity.
Yeah.
Okay, okay, okay. Oh, thank you.
Yeah. All right. So I guess there is no more questions so far. All right. So far so good. So uh, finally, we arrived at the conclusion that the ITG transport reduction is because of the increased zonal shearing effects, and that is because of the enhanced spatiotemporal coherence of the zonal shear. Now, here we are faced with the question again that what sets the strength and coherence of the zonal shear? And that is related to zonal flow saturation in the collisionless regime, and how does shaping affect that? Also, near marginality, uh, how does the physics of limit shift is affected by shaping, and what happens to the zonal flow dynamics as we approach marginality? So these questions are answered in a recent manuscript that is under review in PRL. Hopefully we'll see it soon. So here, the claim is the beneficial effect of anti emerges only well above the marginality. Um, the picture shows the turbulent heat diffusivity versus temperature gradient. And these vertical lines are the marker for a linear threshold, linear growth threshold. So as you can see, anti-diffusivity is lower than PT only if you are sufficiently away from marginality. Near marginality, the two diffusivity curves, they converge. And you can immediately see that the limit shift is less pronounced for anti than for PT. And that is because though the nonlinear threshold is similar for NT and PT, but the linear thresholds are different. So what is the microphysics of this macroscopic trend? To understand this, we looked at the fluctuation and zonal kinetic energy trends, or zonal kinetic energy fraction, and the shearing and effective shearing rates. So this is a busy slide. So the first picture on the left shows the fluctuation kinetic energy and the journal kinetic energy versus A by LT for PT and NT. As you can see, with increasing A by LT, both kinetic energies are increasing. But the journal kinetic energy is higher for PT than for NT. And also the fluctuation kinetic energy is higher for PT than for NT. But if you look at the fraction of the journal kinetic energy to the total kinetic energy, that is sum of journal kinetic energy plus fluctuation kinetic energy, the fraction of the journal kinetic energy that suits up as you approach marginality. At the same time, this fraction remains lower for NT than for PT. The bottom two pictures shows the absolute shearing rate versus A by LT for PT and NT. And the absolute shearing is also higher for NT than for PT away from marginality. And near marginality, they tend to approach each other. But if you normalize absolute shearing by the maximum linear growth rate, this effective shearing increases as you go near marginality. So this tells that the shear suppression becomes stronger near marginality. So here you have already realized that the shearing is higher in NT, whereas the kinetic energy is lower in NT, and vice versa. So next we look at the shearing pattern again across triangularity and across temperature gradient. So the top row is for negative triangularity and the bottom row is for positive triangularity. Compare the pictures, the rightmost pictures. As you go near marginality, you see strongly coherent pillars of shear forming in NT. Okay, so the point is the shearing pattern becomes more and more coherent as the temperature gradient goes down. Also, the shearing becomes more coherent for NT than for PT. So next we quantify the shearing lifetime across triangularity and temperature gradient. So this plot on the left shows the lifetime of the journal shear versus the radial wave number spectrum. And this lifetime is obtained from the exponential decay time of the autocorrelation function for the journal shear for each wave number. So as you can see, the blue curve clarifies that the lifetime of the journal shear is much higher for NT than for PT. And this difference is strong for wave numbers below 1, where the shearing effect is the strongest. The picture on the right shows the relation between the lifetime and the size of the shear, again obtained from the 2D autocorrelation function in X and T. So, and this shows that both lifetime and the size of the radial size of the journal shear is higher for NT than for PT. We can do the same exercise across temperature gradient for fixed triangularity. And as you can see from picture on the left, the lifetime of the journal shear increases across all radial scales as you approach marginality. So this quantification is consistent with the previous 2D pictures of the zonal shearing pattern. So from these pictures, we already have the impression that the zonal shearing pattern is not steady, but it is stochastic, and the quantity to quantify the stochasticity of the zonal shearing is the so-called zonal Kubo number, which is product of the shearing rate times the lifetime of the zonal shear. And this plot shows this Kubo number versus temperature gradient for PT and NT. In either case, the Kubo number is less than 1, which means, again, consistent with the observation that the shearing is stochastic. Further, the Kubo number is for NT is almost 3 times the Kubo number for PT. So that means the shearing is more coherent for NT than for PT. And this again implies more effective shearing in negative triangularity. All right, so far we quantified the coherence of the zonal flow shear, but the question still remains why shearing is more coherent for negative triangularity than for positive triangularity. And here, to answer this, we look at the free energy balance for between turbulence and the zonal subspace more closely. So this is the only slide with equations. So we have to bear with me so that I can explain better the next slides. So first equation is for turbulence free energy balance, which is which shows that the turbulence free energy is generated by the heat flux, which is because of the equilibrium gradient, and it is reduced by the zonal transfer function plus dissipated by if there is any dissipation. And the zonal component of the free energy balance is the second equation, which shows that the zonal free energy increases if the zonal free energy transfer rate is positive or decreases if it is negative. By the way, free energy here, to be precise, consists of the gyrokinetic entropy part, which this quantity Sk is Sk plus Wk, which is the electrostatic part of the energy. They together is one can understand it as the second order expansion of the Boltzmann entropy due to particle distribution function expanded up to the second order. So this Wk, so when you go from the particle coordinate to the gyrokinetic, when you go from particle distribution function to the gyrokinetic distribution function, which is delta Fk here, this electrostatic energy appears as an FLR effect, okay? So the free energy is actually the particle entropy divided, particle entropy times the equilibrium temperature in physical words. So we track the zonal free energy transfer rate, which is tau zonal here. And this is a gyrokinetic extension of the Reynolds power. plus entropy production rate due to fluxes in profiles. So terms like temperature gradient times heat flux, or if there is parallel velocity shear, so parallel velocity shear times parallel momentum flux, like that. So we next look at how this journal free energy transfer function behave as you go across temperature gradient or switch triangularity from PT to NT. So here, I'll take some time to explain these plots. So this journal free energy transfer function, as you can see, is highly intermittent, plus occasionally, while most of the time it is positive, which means free energy is transferred dominantly from turbulence to the journal mode, and so it gives rise to the journal mode and the shear layer, plus corrugations. But occasionally, as you can see, there are events which are going towards the negative side. So focus on the shaded region in either plot. So these are called, I mean, we termed it as a back transfer events, which means occasionally energy or free energy is going from journal mode to turbulence. So it's not, so the shear layers are, so this is again consistent with previous observations that the shear layers are not stationary in time, but they're fluctuating, forming, disappearing. So there is a cycle of birth and death process of the shear formation of the shear layer. Okay, so forward transfer is like birth of a shear layer, and back transfer is like death of the shear layer. Interestingly, in a scan across A by LT, the picture on the left, you can see these back transfer events go down as you approach marginality. And that is again consistent with previous observation that the shear layers are more coherent. So the coherency of the shear layer is determined in a sense by these back transfer events. And I will convince you with more quantification in later slides. So, and the picture on the right shows, again, this journal transfer function for PT and NT. And as you can see, the transfer function is more intermittent and more, and the back transfer events are more stronger for positive triangularity than for negative triangularity. So this is again is alluding to the fact that the shear layers are more coherent for negative triangularity. So the moment there is a back transfer of free energy from journal mode to turbulence, it loses coherence. So looking at the free energy transfer function, its dynamical behavior in the saturated state is a more natural, what shall I say, is a more natural object, I mean, more natural thing than invoking linear KH instability of the shear. So then we quantify these forward and back transfer events across temperature gradient and triangularity. And here is the plot on the left for the mean journal free energy transfer versus temperature gradient for PT and NT. And this transfer is So the forward transfer increases with increasing temperature gradient. That makes sense because the drive gets stronger. At the same time, the forward transfer is higher for positive triangularity than for negative triangularity. Now, this is again consistent with the previous observation that the journal kinetic energy is higher for PT than for NT. Picture on the right shows the radial wave number spectrum of the journal transfer function, the mean journal transfer function, and what we learn from this is that the mean transfer is higher for PT than for NT across all radial scale. So now we look at the more interesting stuff and the new thing, which is the back transfer events, and quantify it across temperature gradient and triangularity. So again, the rate curves here are for rate curve is for the positive triangularity, and the blue is for negative triangularity, and the solid line is for average negative back transfer, and the dashed line is for back transfer fraction. So in either definition of back transfer, the back transfer is higher for PT than for NT. Okay, so that's why the journal shear coherence decreases with increasing A by LT, and so the heat diffusivity increases as you increase the temperature gradient. Now one can see connection between the shear lifetime and these back transfer events, and this plot shows that the journal shear lifetime increases due to the reduced back transfer at lower temperature gradient. So coming to the end, so here is the recap of and the key takeaways. So journal shear layers are dynamic. They form, evolve, merge, split, migrate, and decay. And the journal mode formed due to dominant forward transfer of free energy from turbulence to the journal mode. But at the same time, there are intermittent bursty back transfer events, which act as nonlinear drag. And these back transfer events limit the stability and coherence of the journal flow shear in the turbulent setting. So the real picture is more subtle than the usual tertiary linear cage instability picture. And reduced back transfer leads to more resilient and coherent shear pattern. Near marginality, the back transfer is suppressed. As a result, the journal shear coherence drastically increases, and so the shear layers become more resilient. Now, this leads to new insight into how negative triangularity mitigates ITG turbulence and transport. And this analysis leads to the following bottom-up picture of improved confinement. That is, the reduced back transfer leads to more resilient shear layer with enhanced Kubo number, which causes enhanced shearing efficacy, and that leads to reduced turbulent heat diffusivity. At the same time, there are some observations which goes against the conventional wisdom. Negative triangularity is found to be a state with low journal kinetic energy, but high journal shear. And positive triangularity is a state with high journal kinetic energy, but low journal shear. What matters at the end is the journal shear and not the kinetic energy. While first time it might sound odd, but it's not hard to imagine that you can easily produce a state with high kinetic energy but low shear. So the rigid rotation is a good example of of having a kinetic energy without shear. Another observation that goes against the conventional wisdom is that the weaker zonal residual and yet stronger self-generated zonal shear for NT than for PT. So residual zonal potential doesn't matter. It actually has no physical significance. And in my viewpoint, it's only useful for checking numerical sanity of the code. But wait, why is back transfer reduced for NT? That's the most natural question we are again faced at the end. And the honest answer is that I don't know. But my speculation is that it is likely linked to local magnetic shear reversal at the outboard midplane, as you can see at the bottom picture. This shear reversal is at least responsible for better linear stability, and somehow I think it is also responsible for better stability of the zonal shear for reduced back transfer. So far for the theorist, for the experimentalist in the hall, would be interesting to measure the dispersion spectra of the zonal flow shear, identify different frequency components, their spatiotemporal features, shearing features, look at the signature of propagating zonal shearing fronts, and these studies can be easily done by BS velocimetry. It's not hard to characterize zonal shear coherence for PT and NT from experimental data, and once you do that, then estimate zonal Kubo number. Now, from experiments, it's also possible to analyze these back transfer events. One can look at the time series of the Reynolds power. This is the familiar Reynolds power in the fluid picture, which is in fact a low K approximation of the gyrokinetic transfer function. And one can look at how it varies with triangularity to elucidate the zonal turbulence energy coupling, and BES velocimetry can again be useful here. It's not hard again to quantify the figure of merit, which is shearing times the correlation time, and study correlation length, time, etc., for both fluctuation and the zonal flows. And another useful tool is to do bispectral analysis to study how dominant interactions change with triangularity. So with this, I stop and happy to take questions.
I thank Dr. Rameswar for his informative talk on this triangularity, effect of triangularity on tokamak transport and confinement, as well as turbulence. And he's given a good insight for the experimentalist also. Now this talk is open for questions. You may please raise your hand and ask the question. Unmute yourself and ask the question.
Yeah, Ganesh, go ahead.
Yes, Dr. Ganesh.
Can I go ahead?
Yep.
And ask?
Your voice is breaking, Ganesh. Yeah, go ahead, please.
Yeah, sorry, my connection got out. So
Yeah.
thank you. Very, very interesting talk. So the bottom line seems to be in your argument is that uh, if the zonal shear flow that is generated with certain shearing rate, if it manages to stay put without giving back the energy to the kinetic energy, then you would expect that the effects are benign. And so the number of back transfer rates are minimized, then overall properties go up. And therefore, that's the argument that you have giving, right? So,
Yeah.
what controls the back transfer rate is somehow correlated to the triangularity, which you demonstrated that it happens, but then you sort of the end said that the actual reason uh, could be the geometric effects as you move along the ballooning angle, how the wavelet sees the local magnetic shear. If it sees in the negative triangularity case, it sees a well and a deeper effective negative shear, whereas in the regular one, it is more more around like conventional values. So that typically helps it to suppress back transfer rates. Is that the take home?
Yes, so that's what it has to be. At the end, everything has to be related to the geometry itself, right? Um,
So one related comment is that in your flux tube calculation, uh,
yeah,
the you use an S alpha kind of model. What happens I mean the geometry is what you have a Boozer coordinates, and then you go along the field aligned things. Consider 10 or 20 rho li around the flux tube, so it accommodates the local magnetic shear, right?
yeah, yeah.
So in global calculations, have this been looked at in some sense? I mean, is it worth looking at? That's the question.
It is worth looking at. Yes, why not?
I mean, would you expect some really profound change in terms of, because you have a real magnetic shear, whereas the Q profile would still be positive,
Yeah.
but the wavelets as it moves along between the positive and negative triangularity cases would end up seeing a more deeper well around the ballooning angles, let's say theta zero.
Well, I mean the Q profile is positive. The global shear may itself be positive, but it's still the local shear
Yeah,
is
that's what. So
yeah,
you're saying that the global share wouldn't matter. That's what I was.
yeah. I mean the details depend on the local shear.
Okay, very interesting. Thank you.
Yeah.
I think it would be great to get a copy of the talk if the speaker sort of is okay with it, because we have done some simulations with negative triangularity and positive, and some interesting results happen with the global simulation. Some of
Hmm.
them appear to be in sort of little counterintuitive to what you have got. But then, having said that,
Hmm.
the diagnostics that you have used are um, very focused on extracting the zonal kinetic energy, turbulent kinetic energy. The transfer rates have been calculated using the standard triad model in turbulence. So
Yeah.
we haven't don't have that kind of a diagnostic yet.
Hmm.
So the only thing that we can probably speculate is if you go near the criticality, how does the Dimich shift behave? And is it concurrent in local and global calculations? That's one thing that we can straight away do. So it's very interesting. So
Yeah,
if we can share, if it's okay to share, I'm
sure. Yeah,
asking
yeah. I will.
you
I
and
will. But
Amulya. would be great. Yeah.
I will, but I would like to make comment on damage shift here. The damage
Yeah.
shift is an artifact of the local calculation. Okay.
Okay.
There is no guarantee that you will see a damage shift in global calculation.
Okay. That's interesting.
Yeah, that's a purely artifact.
But
So,
for
so damage shift, though it looks sexy, very interesting thing to study, fundamental, blah blah blah, but it is practically useless concept for fusion
right.
purpose.
Well, it only tells that near the quasi-linear limit, the zonal shearing has an effect on controlling R by LT. That's all it says. You need a higher temperature gradient to push the same amount of turbulence because there's a local shearing, there's a back reaction of the zonal flow. So,
Right. You are never operating near damage shift, right? So it's from practical, I mean, fusion application point of view, nobody cares. But it's a good fundamental physics problem which has no application.
so my question to you, maybe more pertinent question is, I have to go somewhere, so I'm going to ask this question, probably look for your response, and then I'll log out. Unfortunately, I just have to go somewhere. So the point is, I'm beginning to see that uh, from your summary slide that the back transfer rates, any configuration, magnetic global configuration, will, if it reduces the back transfer rate phenomenally, that
Yeah.
is the practical fusion reactor direction.
Yeah.
Because that will stabilize zonal shear flow once it's formed, which will do
Yeah.
all the good things.
Right. So
That's the
shear
take
layers
home.
become,
That's the take
yeah.
home message. And
Yeah.
how do you go about doing it? Is something still not clear? Somehow NT has achieved it, but the physics of that, the exact detail of that, in spite of identifying the basic mechanism, the pathways
Right.
are clear from your work. But how do you control the back transfer is still not clear. Is that correct?
Not clear. So in that direction, we need more, study with more controlled study by manipulating the local magnetic shear structure and do more controlled study of more wide variety of shapes, you know.
So, how about a variational calculation? Can we write down the turbulent free energy and minimize it with respect to the local magnetic shear? And then obtain the best configuration that gives you zero back transfer.
Yeah, isn't that the holy grail? That's the dream, right?
Yeah, but you have the thumb rule, back transfer coefficient.
Yeah, yeah.
So write down the back transfer coefficient in terms of free energy. Minimize local parameter is local delta S cap, variational parameter, and then obtain that configuration where the back transfer is zero.
Well, wonderful. Yeah.
Fantastic talk. I really enjoyed
Yeah,
it. And please share your paper.
sure.
And I will try to send Sagar's recent work on NT and PT. One of our students is going to graduate hopefully soon, another few months. I'll send it. It's a global gyrokinetic calculation which NT and PT, but not the focus is not on this particular aspect, but it has some interesting results. I'll share that with you once.
Yeah, another comment I want to make in passing that um, people have met their careers, in calculating John Residuals, okay, and they have been promoted to leadership positions, they should be
Yeah.
now they should be jobless, they should be removed from this.
They can try now minimize back transfers and get the
Yeah,
job. Yeah.
yeah, get the job back. Yeah, yeah. This is
Thank you,
residual
Rameshwar, and thank
con
you,
the
everyone.
residual potential concept has been around many decades, and Um,
Yeah, I agree.
wasted many lifetimes, I would say.
Okay, I think
Okay.
uh,
Thank you.
I think Prabhakar has a question also. Prabhakar, please unmute yourself. Prabhakar,
Yeah, go ahead.
Prabhakar. I think he has put a question here. No mic with Prabhakar. Okay, is this local shear can help the bootstrap current? And if yes, how much? By how much?
That's a very difficult question. I have no idea.
Okay. Okay. Any more questions? Please raise your hand. So if not, Rameswar, may I ask a question?
Yeah.
That whether the local electric field fluctuations or local electric field shear or a plasma potential shear also can give us information about this back transport or the forward transport.
I mean, yes, in a sense, you have to calculate the Reynolds stress from the local potential fluctuations and then multiply with the journal flow shear to get the Reynolds power, and look at the time series of that Reynolds power and look for signatures of back transfer. Why not? Yes.
Okay. Okay. Thank you. If there are no more questions,
So
yeah.
it's not, so this concept is not um, only for tokamak, it's for any configuration. I mean,
Yes, exactly.
it applies everywhere, even in planetary science, geophysics, astrophysics, whatever.
Okay. So another question: does this study needs a very sharp temperature gradient to have some results which are different from your positive triangularity, or it doesn't have a sharp dependence on your temperature gradients?
It well, the back transfer does depend on temperature gradient. The point is the back transfer is reduced as you reduce the temperature gradient, and when you are above marginality at the stronger temperature gradients, the not only forward transfer is higher, but back transfer is also higher. So that's the point. The shear layers become more incoherent at the stronger drive. Okay, so the shearing efficiency goes down, even though the kinetic energy goes up.
Okay, so one last question, that this A by LT is a significant player in your plots, in your calculations. So how about a fat tokamak? How this physics will behave?
I'm sorry, I didn't get the point. Can you repeat again?
This A by LT is a significant parameter in your calculations, in your plots.
Yeah.
So how this is different from a normal tokamak and a fat tokamak?
Sorry, what's the last word? Which
Fat,
tokamak?
fat tokamak.
Fat tokamak.
Spherical kind. Are you there? Please unmute, Rameswar.
How this happened? Okay, can you hear me again?
Yeah.
Yeah. So what you just need is the temperature gradient variability to see the sensitivity of these back transfer events to temperature gradient, and that you can achieve by increasing or decreasing the input power, right?
Yeah.
So it can be equally done in spherical machines.
Okay, so there is one more question here in the chat box. Theoretically, zonal flow has zero frequency, but in
Yeah.
experiment, it has frequency. What is
Mhm.
the physical reason for this? How it can be different from mean flow shear?
Uh, so zonal flow comes in two flavor. Two coherent flavors. One is the zero frequency zonal flow, other is a finite frequency coherent zonal flow, which is called the geodesic acoustic mode, only seen in toroidal curvature systems like tokamak or whatever. Um, now, so sorry, I missed, what's the other part of the question?
The other part is what is the physical reason for this? How it can be different from a mean flow shear?
Oh, okay. So the mean flow shear is because of the radial force balance of the profiles, like coming from the pressure gradient. Okay. Um, and this zonal flow shear will appear as little corrugations on that mean large scale radial flow shear.
So I think we have no more questions. So yes, you can look into the chat box.
Oh,
There is a reply. But in lab plasma also, it has frequency of few hertz, but it is not GAM.
yeah. Well, I mean, if you do if you do a frequency spectrum of the flow shear, you will see kind of a broadband structure. Okay, in toroidal system, that the width of the frequency spectrum is from zero frequency to the GAM frequency. And in non-toroidal systems, that would be the width would be narrower, but still there are always finite frequency component. There are continuum of finite frequency components, which gives rise to the stochastic effect that we discussed. Okay. So what gives rise to this finite frequency? Uh, don't know, to be frank.
Okay, I think
So naively, turbulence must uh, give rise to some kind of elasticity to the zonal flow, okay, so that it bounces back and forth. But what's the mechanism for producing this elasticity is nobody knows. So from theoretical point of view, there is a whole world of problem to be done.
okay. So I think yes. So he's happy. So I think if there are no more questions, we should thank Dr. Rameswar again, and we should close the meeting. Dr. Rameswar, if you have any last words to convey to us.
Well, thank you very much for giving this second opportunity to present the work and gathering audience for discussion. Uh, and of course, thank you very much to IPR for giving this platform, and IIT Jammu for doing the hard work behind. okay, for felicitating the system. Okay. Thanks again. Thank you, everyone involved.
Okay, thanks, Rameswar. Hope to see you soon around.
Sure.
Okay, see you again. Bye.
Bye-bye.